A very good morning, everyone, and we'll just pick up from where we stopped last time. In our last lecture, we tried to emphasize some of the basic postulates, and then went on to make mention of a few details in relation to quantum electronics. And today, we'll just run through, probably, let's say, we'll make a quick recap. Okay, let's move this. Review. Postulates. So in our last lecture, we mentioned that the state of a dynamic system is completely specified by the state function, say psi of st, okay? Where this is a state function. And should we refer to this in the Hilbert space, then we could also address this as the ket psi, okay, in the Hilbert space. Meaning that at every time t, for instance, the state of a physical system is defined by the state function, okay? Then we also made mention that all physical observable properties of a dynamic system are represented by some dynamic variables that are the linear operator, which we denote as the parameter hat, okay, where we have a hat to it. And then we went on to mention that the necessary and sufficient condition for any two observables to be simultaneously and precisely measurable is that their respective operators commute. That is, when we have the quantum bracket of two operators, A and B, for instance, should we take the difference of these two operators applied in a different order, say A hat, B hat, minus B hat, A hat, then this should be zero, meaning the two operators commute, okay? And when the commutator between the two operators is not the same as zero, we will say they don't commute. Okay. Now, we also mentioned that in classical mechanics, that the commutator of, say, the position and momentum is the same as zero, meaning they can be measured simultaneously and precisely. But the reverse is the same. When we now have to relate with these two variables in quantum mechanics. So we're also able to show that the commutator between the position and the momentum, which is the same as zero in classical mechanics, does not hold true in quantum mechanics. So what did we now make mention of? Now, in quantum mechanics, we were able to show that the product operator operating on the state function, say the momentum operator and the position operator operating on the state function is the same. Now recall that from the postulate that the momentum dx hat is the same as negative j, where j is the complex quantity, h cross d dx. So once we plug that in, then we'll be able to expand this entire process to be the same as negative j h cross d dx, which is a momentum, and then x, which is the position. And we made mention that x, they are more like the operator are the same. But when we talk in terms of the Cartesian coordinate, then we have to represent the momentum with the differential. Okay? And then this now operates on the state function. Okay. So we also were able to show that this is the same as negative j h cross d dx operating on x psi of x. So where with the product rule, we could resolve this, right? Product rule, where we say something like u dv minus v du, because we have x, the position and the state function are functions of x. So then we could differentiate. And when we do that, we now have that this operator, the product operator operating on the state function is the same as negative j h cross s d dx psi of x. That is u x dv times this. Then we're going to add that plus v du, where v is psi of x. So we say negative j h cross psi of x, then du, that's the x dx. So this is going to reduce to 1. And then this entire process is going to give us negative j h cross x d dx psi of x minus j h cross psi of x. And then we now have that the momentum operator, position operator psi of x is the same as negative j h cross s d dx psi of x minus j h cross as this process psi of x. And now this will truncate this and will truncate this, so that we now have this to be the same as p s hat is the same as negative j h cross s d dx minus j h cross. Okay, and now we can also represent this, let's say by rearranging. We say that s hat is the same as x dot. So we just bring out the x. So we separate it from the momentum expression, which is negative j h cross d dx minus j h cross. Now this is going to be the same as p hat x s hat, which is the same as s hat p s hat, which is, okay, let's not equate it yet, which will be minus j h cross. Okay, now this is going to be the same as P S hat minus S hat PS hat, which is equal to minus J H cross. Now, if we say multiply through by the negative, then we have S hat PS hat minus PS hat S hat is equal to JH cross. Now, this is the same as the quantum product between X hat PS hat, which is the commutator. And we now see that the commutator is a non-zero value such that the commutator between the position and the momentum is the same as S hat PS hat minus PS hat S hat is the same as JH cross, meaning the position and the momentum do not commute, do not commute. Okay, because it gives us the commutator gives a non-zero value. We're able to show this last time in quantum mechanics. And then if we now evoke the Schwarz inequality, then the Schwarz inequality, then we can therefore say that the product of uncertainty of any two operators, say A and B, is always equal to or greater than 1/2 of the magnitude of the expectation value of the commutator, which gives us the quantum bracket of the two operators. And this is usually approximately equal to 1/2 of the expectation of the resulting value. So this therefore implies that, recall that the commutator between the position and the
where are you doing
is the same
no
as JH cross, right? So by the Schwarz inequality, we now have that the product of the uncertainty between the position and the momentum is greater than or equal to, now we are taking the magnitude. So the magnitude of this expression is going to give us H cross. So it's going to be greater than or equal to 1/2 of that parameter, which is H cross over 2. And should we consider in the Y direction, then we are going to get the same thing. H cross over 2. And in the Z direction, will be greater than or equal to H cross over 2. And this therefore engenders the statement by Heisenberg. And Heisenberg's uncertainty principle therefore states that it is not possible to know or specify the position and the momentum in the same direction of the particle simultaneously and precisely. So the point now is, the more we know one, the less we know about the other, which is a clear distinction between the classical and the quantum mechanical perspectives. And we're also able to show that since the operator operating on an arbitrary state function changes it to another state function, therefore, that is, let's say we have this operator operating on, okay, let's not use psi this time. Let's just use some arbitrary parameter, operates on this function, then we're made to understand that this operator is going to transform this operator to something else, to some other function, okay? This function. So the operator operating on this function is going to transform this to some other function, which we can call a state function. And then there is a value that is associated with this state function, which we call the eigenvalue. And this is only possible because this is now a unique set of characteristic state function that will not change when operated upon by the operator. And that is why they are called the eigenfunction, which we mentioned earlier. And then the characteristic number that corresponds to each of the eigenfunction is the eigenvalue. Now, this will be very, very important when we begin to describe the Hamiltonian, for which the eigenvalue becomes the energy, E, which we are going to see shortly. And then we also made mention that, that the state function satisfies the time-dependent Schrodinger equation. And there, we show that the Schrodinger equation of motion to be given as the h cross squared over 2m, then the Laplacian psi plus the potential energy vector or operator, psi being the same as the negative jh cross the psi dt, which is the time dependent Schrodinger equation. Okay. And then for us to be able to derive the time-independent Schrodinger equation, so let's assume that psi r of t is the same as u of r g of t. Okay. Now, so that the time-dependent Schrodinger equation will now become, should we plug this into psi, we now have negative h cross over 2m Nambla squared u of r g of t plus v of r u of r g of t will be the same as j h cross d dt u of r g of t. Okay. And now if we rearrange, then we are going to have negative h cross squared over 2m Nambla squared u of r plus v of r u of r into bracket g of t is the same as jh cross the g of t, because g of t is a function of time, the t, then u of r, which is not a function of time. Recall, what we are trying to do is to derive the time independent Schrodinger equation. We already know the time-dependent Schrodinger equation. So, and then we can now rearrange this We say, well, negative h cross squared over 2m lambda squared u of r plus v of r u of r is the same as j h cross over g of t, because we just move this, then the g of t, more like collecting like terms, the t u of r, okay? Now, we can equally represent this the same to imply 1 over u of r. Should we move this so we know we just collected like terms? Negative h cross squared over 2m lambda squared u of r plus v of r u of r, which is the same as j h cross over g of t, the g of t dt. Okay? Now, you will recall that we once mentioned that the Hamiltonian is the same as the energy, that is E is the same as negative h cross squared over 2m lambda squared plus the potential operator, which is the same as j h cross d dt. Okay? So if this is true, then you will observe that in this operation, is similar to this operation, to the Schrodinger equation. This and this. And if we should pull this out and then exclude this, more like we want to exclude this, and then take note of this, because once we pull this out, that is, let's just, let me show you, this is the same as h cross squared over 2m lambda squared u of r. No, I want to bring out a u of r coming from this plus v of r. This is 1 over u of r. Then once we bring this out, this is u of r. Then this would be j h cross g of t d dt dt. And then we can cross this out. And then this is the same as this. Okay? Now, if we cross this out, then negative h cross squared over 2m lambda squared plus v of r is the same as j h cross over g of t d g of t dt, right? And now recall that we made mention in our earlier class that the energy is the same as the sum of the kinetic energy, which is this, and the potential energy. And should we knock off the state function, then we see that this expression is the same as negative, this is negative, please, is the same as negative JH d theta, d dt. Okay? And then, no, there's no negative here. That's on the other side for the Schrodinger equation, right? There's no negative. So what of J H cross, yeah. Okay. Now, by observation, you will see that going by this analogy, then we can also state that the energy E is the same as negative h cross squared over 2m lambda squared plus v of r, which is the same as this expression. JH cross over G of T, the G of T, dt. Okay. Now, okay, we have a few notes here. Why did the sign of the RHS after the assumption change? So I didn't get that. So what are we trying to derive from this equation? Okay, yeah, we're trying to derive the time-independent Schrodinger equation. So far, we've been playing with the time-dependent Schrodinger equation where we see that all of these depends on the time. So we want to try to derive the time-independent Schrodinger equation, which is not dependent on time. And so far, you see that we have been able to arrive at this. So we now need to solve this solution, okay? So for us to be able to solve this solution, okay, so let us, now with this, and coming to, okay, now with this, we can now rewrite this expression because the energy is seen to be the same as this expression, okay? So it means that the whole of this expression is the same as E U of R. So for us to now put up, okay, let us write this. So it means that we now have negative H cross squared over 2m lambda squared plus V of R, U of R is the same as E U of R. You will recall that we already showed that E is the same as JH cross over G of T, the G of T dt, okay? So now that we have been able to put up this expression, this is the time independent Schrodinger equation. And looking at this closely, you will observe that we do not have any component of time given the energy in this case. Okay? And here, U of R is the eigenfunction of the Hamiltonian. And we already know that E, in this case, is the eigenvalue of the Hamiltonian, and it must have a real value, okay? And is we could classify E, in this case, as a member of the Hermitian operator, okay? Now, it should be noted that this eigenfunction is the solution of the time-independent Schrodinger equation, okay? So this is the solution of the time-independent Schrodinger equation. Okay. And another interesting point is that this can equally be represented, that is, okay, let's take it gradually so we don't get things, let's take it gradually because we're going to relate the eigenfunction to the energy, okay? So in this case, we already know, just like I mentioned, that the set of allowed values of E are the eigenvalues, and they are actually evaluated by the boundary conditions, you know, of the eigenfunction. Okay. Now that we have resolved that, we still have one more problem to solve, and that is E. Okay, the energy. Because what we are really interested in as far as this function is concerned is the energy, because we already know that if we're able to characterize that property, then we should be able to tell everything we need to know about that particular particle. And this will build the foundation for the fabrication of your electronic devices, especially high-speed electronic devices, which we are going to mention today, because we'll gradually move off the abstract domain into something a little practical today. Okay? Now, for us to be able to find the solution, so let us, we need some space. We are going to be doing what you already know, because you already played with this technique in, okay, E is the same as in your fundamentals of electrical engineering, when you resolve first order and second order circuits, okay? And then you had to deal with first order and second order differential equations. And in this case, we are going to be dealing with the first order. And when we get into the wave-particle duality, then we are going to solve the second order equation, but it's about the same, okay? So nothing to worry about. Now, you'll observe that this is a first order differential equation. And from your understanding in transient analysis, you already know the solution. So the solution of your first order differential equation, in this case, where we have the g of t dt, is going to give us g of t being the same as the initial value exponential. Here we're going to have a negative. Well, let's leave that. We're going to have a parameter dt. Let's leave the. It's going to give us a negative je over the over h cross, but let's leave that. So we're going to have some parameter t. So this is how this general solution will look like. Okay. When you resolve your first order differential equation. Okay. So let's assume we have one storage element in the circuit. Okay, and then you have to resolve that. So it's going to lead to this, and then you solve your first order. And the general solution will give you something like this. Well, let us resolve this, okay? So what's going to be the general solution? Let's partition this board. So have more space. This should do. Okay. Now, from this expression, we can now tell that, let's rearrange E over JH cross is going to be the same as 1 over G of T, the G of T dt. Okay? And now this is going to give us the same as J to rationalize J times JH cross, which is the same as the G of T over G of T dot 1 over the T, right? So this is going to give us J E over J squared H cross, which is the same as the G of T over G of T dot 1 over the T. And this is now going to give us negative J squared as negative J E over H cross, which is the same as the G of T over G of T dot 1 over the T. Now, this is going to give us, we're just trying to solve what you already know, solving the differential equation, E over H cross. multiplied by dt. dt is going to be the same as the g of t over g of t. So if we integrate both sides, so we are going to have integral, negative j e over h cross dt is the same as integral the g of t, g of t. So this is going to give us negative j e over h cross integral dt, which will be the same as integral 1 over g of t, the g of t, all right? And this is going to give us negative j e over h cross t, right? Plus some constant, say c, which will be the same as, now, if we integrate 1 over some parameter, we're going to get a natural logarithm, which is ln g of t. Okay? Now, if let's assume that c is also takes on the value having the natural logarithm of, say, ln a. Don't forget that the natural logarithm is the same as log to base e, right? You already know that, right? Log to base e. Now I just saw a comment. What is E? That's the energy. The energy. Okay? E is the energy. That's what we've been talking about for quite some time now. Okay? Which we can get from the Hamiltonian. So so if C is the same as the natural logarithm of A, then we have that once we plug that into this, so we have that negative J is the same as E over H cross T plus ln A is the same as natural logarithm G of T. So this is going to give us negative J E over H cross T, which is the same as ln G of T minus ln A. And this will give us negative J E over H cross T, which is the same as ln G of T divided by A. So now this is the same as saying negative J over H cross T is the same as log to base E G of T over A, right? And now, if we convert from the logarithmic function to index form, so we want to convert from logarithmic form to index form. Recall your regular indices and all that. So we are going to have that G of T over A will be the same as epsilon to the power of negative J E H cross T. Okay? And then G of T will now give us A epsilon minus J E over H cross T, which is the same as the general solution for the first order differential equation. Okay? Now, but what is A? What is A? So we need to resolve the value of A. We can't just assume it's... So now, if we consider the initial boundary condition, that is at T equal to 0, then at T equal to 0, so we have G of 0 will be the same as A, epsilon T is the same as 0, so this expression reduces to 0, epsilon 0. So that's going to give us A times 1, which is equal to A. So meaning A is actually the initial value, okay, of this state function. So G of T, therefore, will now be the same as G of naught epsilon, that's at T greater than 0, minus J E over H cross T. So that is the solution. Okay? Now, we assume, now if we assume that the set, that is this set, which we said is the eigenfunction. Now, if u of e of r is the same as psi of e of r is generated by the time independent Schrodinger equation. Now recall that we made mention already, we already showed that the time independent Schrodinger equation in the previous slide is given us, is given us negative h cross squared over 2m lambda squared, then plus v of r u of r is the same as e u of r. Okay, we already showed this. So we are now saying that we want to assume that this set u of e of r, which is the same as size of e of r, is generated by this time-independent Schrodinger equation. Then we are going to have that this time-independent Schrodinger equation will now be represented as negative h cross squared over 2m lambda squared plus v of r u of e of r will be the same as e u of e, u sub e of r. Then alternatively, we can also put it this way. Alternatively, we can also put it this way, negative h cross squared over 2m lambda squared plus v of r psi of e of r, which is the same as e psi of e of r. So we're actually saying the same thing. Okay. Now, if this is clear, then you will recall that the probability density function is given as what? Now, if this is the eigenstate, so the probability density function of this eigenstate is going to give us u of e r of r conjugate times u of e r. Yeah, that is the probability density function. The probability of getting a particle within that spatial range, right? Now, let us clear this and then, so it means that the probability density function is the same as u of e conjugate of r, then u of e of r, which is the same as the modulus of u of e of r squared, right? We've already done that before. And then the total probability of finding a particle within that volume will be the same as the integral of the mod u of e of r squared dv, which is the same as 1. It means we'll find a particle within that spatial range. Now, there's something you should take note here, that the normalization of psi of rt, which is the time-dependent Schrodinger equation, is achieved by requiring that the initial condition or the initial value of this function, the conjugate times its value, should be the same as 1, which is the same as the PDF, right? Which is same as g of phi naught squared, which is equal to 1. And then that means this is also the same as the integral of the mod e of r squared dv, which is the same as integral mod u of e of r squared dv. Okay. So therefore, with this, we can now conclude that U of E R epsilon minus J E over H cross T is a particular normalized solution of the time-dependent wave equation. Okay? So hence, the time dependence of the solution of the time-independent Schrodinger equation will now become this. So let me put that down. So you need to absorb that. So from the foregoing, the time dependence of the solution of the time-independent Schrodinger equation becomes psi of En RT is the same as U of En of R epsilon minus J E H cross T, which is the same as psi of En of R epsilon minus J E over H cross T. Now, please take note of this expression, okay? Which is the time dependence of the solution of the time-independent Schrodinger equation. Now, when we get to the wave-particle duality, then we are still going to come to it, okay? Then we'll still have to play with this. Okay. So, the idea now is that at time t equal to 0, the system is in a particular eigenstate. Okay? Now, when t is the same as 0, then we see that this particular system is going to be in a particular eigenstate, U of E naught of the Hamiltonian, corresponding to the eigenvalue E sub n. Okay? So this implies that the eigenstate of the Hamiltonian is referred to as stationary state. Because at some point we are going to see shortly when we get to quantum wells that this n could take on some value, some integer value, 1, 2, 3, such that should we have this, then probably my E1 is here, E2 is here, all the way, you know, and then we're able to tell the energy band gaps. So this is where the reasoning comes from, okay? And we are going to show that when we begin to deal with systems where we have to relate with the wave transition from one boundary to another. But in the first instance, we are going to cover wave in free space, you know, just in a vacuum, you know, without boundaries, okay? So what we are not trying to say is that the implication of this time dependence of the solution of the time-independent Schrodinger equation implies that the eigenstate, let me write that down, that the this implies, let's put it that way. Now, this implies that the eigenstate of the Hamiltonian is referred to as the stationary state of the system. Since all observables are independent of time. So you should know that the understanding of the structure and characteristics of all matter is profoundly affected by the fact that the eigenstates of the Hamiltonian are stationary states of the system. And as such, this helps us to identify individual energy states. Okay? As we will see shortly. Okay? So if we now take the expectation value of the Hamiltonian, which is negative h cross over 2m Nambla squared. No, that's not there. 2m Nambla squared. And of the potential plus the potential will be the same as J H E to T is going to give us the energy value. Okay. Perfect. Now that we have been able to review all that we already discussed, so now we will have to come to the ideology, which we usually attribute to the Broglie, which is the wave particle duality. Well, I would not want to bore you with the physical perspective and the history, which we covered in the video you already have online, but we'll just go straight, coming from what we just did, okay, in resolving the differential equation. So if, for instance, we are given a particle of, say, mass m, okay, we have a particle, and this particle has a mass m, and it's moving in free space. It's not bounded in some material medium, okay? It's just in free space or in vacuum. And it has a velocity v sub x. Or better still, linear momentum p sub s, which is the same as m v sub s. The idea is, what could be the possible state function of this particle in motion in free space? So when we look up the postulates, the state function must be the eigenfunction corresponding to the eigenvalue, which can be a positive or a negative value of the operator of this momentum. Okay? Representing the position component of that linear momentum. So if we describe this mathematically, then we now see that the operator, the momentum operator operating on the state function, gives us an eigenfunction, it's like p of x, with an associated eigenvalue. Okay? And from the corollary 2, we made mention that the momentum operator can be represented by its differential component, right? So with this, we should be able to resolve this so that this expression will now become, by replacing the momentum operator, will now become negative j h cross d dx psi p sub s of x is the same as p of x psi p sub s of x. And once again, we can rearrange, and then we already know what the solution will be. Because by rearranging this, we are going to have, if we call it like terms, so we are going to have the psi p of s of x divided by psi p sub s, just the way we resolved the previous one, will be the same as p of x divided by negative j h cross, right? then dx. So this is going to give us a first order differential. So we can also resolve this, but the difference now is we have a negative here. So we didn't have a negative in the order. So the solution had a negative. So this time the solution won't have a negative. The solution will be, once you resolve this, g of s of x will be the same as some constant epsilon j. Let's put that down. J p sub x over h cross s, because this is not the t, this is the x, right? In the previous case, we resolved the differential with respect to time, but this is with respect to position. So this solution follows directly, okay? So we don't have to begin to resolve everything again. Now, this here is a constant to be determined by the normalization condition, okay? But the point here is that this particle is in free space, so it means there are no boundaries. So we cannot define boundary conditions like we described in the first case and said, well, at t equal to 0, initial boundary condition, okay? Then as we progress to some other time, t greater or equal to 0, but this is not possible here, okay? Because the entire description has no boundaries, let's put it that way. So no boundary conditions. And then the velocity or momentum of the particle can have any value, and it's a continuous eigenvalue of the operator, of the momentum operator, okay? Now, if that is clear, then the probability density function, the PDF, which is the same as mod of p sub psi p sub s of x all squared, is going to give us the mod of the constant, okay? Because once we take the mod of this entire process, so whatsoever we're going to get is going to be the mod of the magnitude of this, which is mod c squared, okay? And you should know that the PDF is a constant independent of position, because here it's not a function of position, but the state function is a function of the position, okay? So this implies that the particle could be anywhere since it is independent of the position x. And if we put this differently, you recall Heisenberg uncertainty principle. And going by Heisenberg's uncertainty principle, if the linear momentum of the particle is known precisely to be of value p sub s, which is the linear momentum, or the uncertainty is the same as 0, that is, delta p sub s is the same as 0, for instance, then the uncertainty in the position, delta s, must be infinite, because they don't commute, meaning the more we know one, the less we know about the other, okay? Now, if that is clear, then it means that the particle can be anywhere with equal probability. Now, don't forget, we are interacting with this particle relative to free space. And you also recall that in quantum mechanics, a particle traveling with a constant velocity, say v sub x, okay, it's traveling with the constant velocity, v sub s, always means an ensemble of similarly prepared particles, all in the same state of having the same linear momentum, okay? So it means they all have the same linear momentum, which is same as n v sub s. And I also want you to recall at this point that the uncertainty principle states that it is fundamentally not possible to specify the position and the velocity precisely simultaneously. So since c can be fixed by the normalization condition, so we can consider that if we have a single particle, for instance, between that spatial range from, say, for which s can take on value from -infinity to some value say positive infinity. Now, since this distribution function is independent of the position, then it means that the PDF will be zero. Will be zero. It won't be one. And what if there are n particles per unit length in that spatial range? Or say one particle. So if we consider one particle within the spatial range where we have n particles, so that one particle will be described as 1 over n. Okay? And then we can now describe our PDF to be mod c squared over n, the total number of particles, which gives us, we're going to integrate over one particle, that's 0 to 1 over n, mod p sub s of x dx. This is going to give us 1 because there's a probability that we'll find one particle by estimating the total probability. And then it means that 1 is the same as c mod squared over n. So in this case, you will see or observe that c is the same as square root of n because 1 is the same as c squared over n. So c mod squared is equal to n. So c is the same as square root of n. So, okay. So now that we have been able to resolve that, let's not forget this expression, okay? So once we pull this up again, so it means that we have psi p sub s of s, is the same as c exponential j p sub x, p sub s over h cross x. And we already know that c is the same as square root of n, which is the amplitude or magnitude of the amplitude. So we now have the solution that this is the same as square root of n epsilon j p sub x over h cross s. Now, this state function describes a beam of n particles, okay? This describes a beam of n particles per unit length. With a constant velocity. So if we already know that the momentum is the same as the mass times the velocity, so the constant velocity v sub s will be the same as the momentum divided by the mass. Okay? And for the free particle, the Hamiltonian will be described by the kinetic energy, not the potential energy. So it means that the Hamiltonian will be the same as the potential energy over 2m, which is the same as negative h cross squared over 2m d squared dx squared. So with this, the corresponding time-independent Schrodinger equation will now become h cross psi of e of x will be the same as negative h cross squared over 2m d squared dx squared psi of e of x, which is the same as e psi of e. Okay. So this becomes the Schrodinger time-independent equation. Okay. Now we have, say this is equation 1, then this is equation 2. Mhm. Now, what will happen if we plug in equation 1, for instance, into 2? Okay? Now, if we do that, it will show that it is also an eigenfunction of the Hamiltonian. Okay? So, therefore, we now see, let's put this, that psi of E of x is the same as square root of n epsilon j piece of x over h cross s. And now this corresponds to the eigenvalue E to be the same as piece of x squared over 2m. And this is an important metric because p of x squared is the same as 2me. And this also is the same as piece of x, which is the same as square root of 2me. Okay, so the momentum is directly related to the energy, where E in this case is continuous. It's not quantized because it's in free space. So the energy is continuous. It's not quantized. You have to take note. Okay, so the energy of a particle in free space is not quantized since the momentum is not quantized. It's a continuous value. Now, since we already know or have that the state function is an eigenfunction, of the Hamiltonian, then the energy and the linear momentum of this particle in this state can be known simultaneously and precisely. Okay? So you should take note. The energy and the linear momentum commute. That's the implication. So the Hamiltonian, or the energy, and the linear momentum, can say they are directly related. They commute. Okay? That is this negative h cross squared over 2m d squared dx squared minus j h cross d ds is equal to 0. And you'll observe that all the parameters except the constant h cross squared over 2m are included. So h cross is here in the momentum, in the energy, h cross is there, d dt, and all of that, so they commute. Okay? Okay. Now, it should be noted that the knowledge of the eigenfunction of the Hamiltonian implies that it is possible to find the solution of the corresponding time-dependent Schrodinger equation, or the time dependence of the state function. Okay? Or better still, this. And if we now do that, then we now look at the time dependence, that is psi e of st, will now give us an expression that is similar to that of a monochromatic wave, where we can now tell the propagation constant and the frequency component. And this is going to give us square root of n epsilon j p of x over h cross x minus j e over h cross t. Now, well, from the electromagnetic wave, which you ought to have reviewed by now, we know that for a plane monochromatic wave, now it is monochromatic because it has one frequency, because the word chromatos, from which we have chromatic, is color, right? So it all that this tries to say is that for the electromagnetic wave spectrum, each spectrum have a color. Okay. either visible or invisible, okay? So we have the visible light spectrum anyway. So they all have their colors, and these colors are related to their wavelengths, okay? But if we now consider a plane wave with just one frequency component, then we see that, well, by standard, from electromagnetic wave, this is described as root n epsilon j k sub x s minus j omega t. Okay, this is a description of a plane monochromatic wave. And now, in considering our expression for the time-dependent solution, this is what we have. And when we compare this expression with the plane monochromatic wave, we see that they are similar in the sense that this expression here is similar to this expression, and this expression is similar to this expression. And if that is true, because here, this has an amplitude. The amplitude here is root square root of n. That's the amplitude, okay? That's the amplitude. Now, in comparing this, we can now extract these parameters to form some mathematical basis, which Einstein was able to play with. And then we now see how this relates to the derivation of the Einstein's photon model. Okay? Here we know that K sub s is the propagation constant. Propagation constant. Okay? Or you could call it wave number. Okay? Wave number. And it tells how the wave propagates in space. Okay? And it is usually the same as 2 pi over lambda. Okay? And it actually measures, or better still, it is a measure of the number of wavelengths per unit distance, okay, measured in radians per second. That is a propagation constant. Then we have the angular frequency, omega. So omega is the angular frequency. And you already know that omega is the same as 2 pi f. Okay? So now, let us come back to a time-dependent solution, okay, which is of this form, which we could derive the way we resolved our first-order differential equation. So it's not a big deal. Now, from this, we know that the propagation constant, K sub x, will be the same as P sub x over H cross. Okay? And then the angular frequency, or better still, the frequency is 1. And then the frequency will be the same as omega, okay? As omega will be the same as E over H cross. So these are two important parameters. Okay, we already know omega is 2 pi f. So if we say 2 pi f is the same as E over H cross, so what do we get? So it means that now we also know that H cross is the reduced Planck constant, which is H over 2 pi, right? H over 2 pi. Now, if we plug that in, so it means that we have from this, we have 2 pi f is the same as E over H over 2 pi. Okay? So this now will give us 2 pi f is the same as 2 pi E over H. So this will cross this. So this is going to give us F is equal to E over H. Okay? And now, this is what Einstein postulated. E is the same as HF, which is the Einstein photon model. Okay, where E is the energy of the photon, and H is the Planck constant, and F is the frequency. Now, you will recall that, okay, let's write this. So we already know that E is the same as HF. Now, you will recall that C is the same as lambda F, okay? And therefore, E will now be the same as HC over lambda. Now, if we recall the, what's it called now? Special relativity model, okay? Now, the special relativity model states that special relativity model is given as E squared equal to E naught squared plus Px squared C squared, okay? Where E naught squared will now give us M naught C squared or squared plus Px squared C squared, okay? So here, M naught is called the rest mass, okay? M naught is the rest mass. And particles that travel at the speed of light have zero rest mass, okay? And now we are considering this particle. So photons have zero rest mass, okay? So M naught is equal to 0 because particles that travels at the speed of light have zero rest mass, okay? So that this expression, the special relativity expression is squared, we now reduce, so it means this will reduce to 0. 0 times all of this. We now reduce to Px squared C squared. And then this is going to be the same as E equal to Pxc. And then P sub x, the momentum is going to be the energy over C. So E is going to be Pxc. So this relationship is equally very important. Okay? It's equally very, very important. Largely because this relationship shows that a massless particle still has energy and momentum. Okay? So here, because we are considering a massless particle, because photons are massless. So they have, because the idea is for the rest mass to be equal to 0, so it means that that particle is massless, okay? It means that the particle is massless. And this expression now tells us that a particle that is massless still has energy and momentum, okay? And now, from our derivation, we can now see that P sub SC is the same as this energy. This is also energy, so the equivalent is the same as HC over lambda. Okay, so this crosses this such that the momentum is the same as the Planck constant divided by the wavelength. Okay? So, going by this, we have two fundamental expressions from what Einstein played with. That is this expression and the photon energy expression. There are two very important parameters. Now you observe that the energy and the momentum has to do with the particles, And then the wavelength and the frequency is a wave property. It's a wave property. So this is where the particle wave duality concept came into play. That a particle also exhibits some wave tendencies. And a wave, the wave property of a particle also exhibits some kind of particle property. Hence, the Broglie, that is the, let's wipe this, the Broglie, therefore assume that these two properties hold for all matter particles, including the electron. The wave particle duality. So the Broglie proposed that for a matter particle with momentum, say p sub x, you can actually associate a wavelength, say lambda d equal to Planck constant divided by p sub x. This equation actually predicts the Broglie wavelength of a matter wave is associated with the motion of the material particle with this momentum, p sub x. So it should be noted that the probability density function, which we talked about earlier, is the same as the total number of particles. And this is the intensity of the wave. Now, we already know that the state function links particle and wave properties. Okay, so we can now call this particle, or better still, the state function, matter wave or the de Broglie wave. So the state function can also be referred to as the wave function. And going by the de Broglie wavelength, we already know that lambda, going by our original deduction, because we showed that the momentum is the same as 2 pi over lambda, right? So we now be 2 pi over p sub x. And now we know what p sub x is relative to the Planck constant by this expression, okay? So, okay, sorry, this is the wave number, right? This is the wave number. And then let's position this very well. Let me put this. This is the wave number. That is what we showed when we talked about the monochromatic plane wave, okay? So it means that this lambda will be the same as 2 pi k sub s, right? Which is the wave number, okay? So we have k sub x, okay? And now we know that this is 2 pi over, and we also show that k sub s is the same as p sub x over h cross when we try to compare our solution with the plane wave. So we can plug that into this p sub s over h cross. Then this is going to give us 2 pi h cross over p sub x, okay? And now we know h cross is h over, so, and h cross is reduced Planck constant. So that's 2 pi dot h over 2 pi divided by p sub s, which is h over p sub x. And we already show that p sub s is related with the energy as the square root of 2m over e. So this is going to give us h over square root of 2m e, okay? So it means that the de Broglie wavelength is related to the energy of the wave, okay? So this is in free space. So should the particle be traveling in a region of constant potential energy other than free space? Because this statement will be put to use when we begin to play with quantum wells. then what will happen to the wavelength? So the wavelength at that instance will be a difference of this energy and the potential. So let us designate that. So when a particle is traveling in a region, because so far we've been talking about free space in a region of constant potential energy V, other than free space, the Broglie wavelength will become lambda d equal to h over square root of 2m e minus b. Please take note of this expression. It's going to be put to use very soon. Okay. So, okay, that is that. So, well, there are some other details. I'll spare you at this point because we already have them in the video. So I will not want to overflog the importance of those right now. Now, I just made mention of something. So we've gradually moved from free space to bounded regions. And this brings us to quantum wells. Perfect. Now, like I mentioned earlier, well, we are going to be moving off a little from the abstract domain into something practical. We've been talking about all of the Schrodinger equations and all of that. And the idea is we want to be able to analyze the properties of particles, okay, in some medium. And should we attempt to do that, understanding the nature of atoms, we know, well, we have some bounded electrons. And at some point, we want to either excite them, we want to displace them. So it's either they are releasing energy or they are absorbing energy. And largely because they are very small, microscopic, then their behavior in terms of localization becomes very random. And your guess will be as good as mine. The smaller a particle in space, the more random it will behave, okay? So as such, you see a particle so tiny in this dimension relative to a larger space, now begins to move in a random position and it moves very fast, okay? And why does it move very fast? Because the mass is relatively small. Okay. Now, what do we mean by quantum wells? Now, I just made mention of the motion of this particle, which is characterized by the Schrodinger equation in free space. And now we want to consider what will happen to that particle if it's bounded. And if it's bounded in a well that looks like this. So it means that we can tell that this is region 1, this is region 2, and this is region 3. Should region 1 and region 3 be the same, then region 2 obviously won't be the same. And as such, we now want to tell what will happen should this particle drift into this well. What is going to happen at this point? Okay, there's a question here. Does it mean when a particle is in free space, potential energy is zero? That is what we, showed in our analogy. In our analogy, okay? Going by what we already played with, because it's in free space, it's in motion, and for a massless particle, it is random and constantly moving. And this will become evident when we get to solid state physics, when we begin to play with your semiconductor devices and the energy levels, the Fermi levels, okay? And we'll begin to talk about the density of states, okay? That's where the application of this domain becomes very, very relevant. But well, at this point, I'm not going to go way into this so you don't get saturated. But we are going to. I just want to introduce this. Okay. So when we consider the state function of this particle moving in this dimension, then it gets into this confinement. So it means that we are able to confine some of these particles in this state, in this region. Now, it will require some amount of energy for this particle to be able to escape this confinement into this dimension. Okay? So, and as such, between this dimension and this dimension, we have boundaries. So we are going to be resolving some boundary conditions. Okay? We are going to be resolving some boundary conditions. So on a lighter note, when we talk about quantum wells, what do we mean? Okay, so it actually means that we are actually combining different materials. Now you recall that in your periodic table, we have, okay, let's look at the elements in group 3, 4, and 5, okay? They are very important to us in semiconductor physics, okay? Now, you already know that in your group 4, we have carbon, we have silicon, we also have germanium, okay? And all the way, okay? Now, also in, well, all the way. So, but silicon and germanium are two elements you have been playing with, and you know where we use them for semiconductor devices, but because of the temperature sensitivity of germanium, silicon is preferred, right? Good, that's what you've been told. Well, we are not into the devices, but rather we want to know how these particles operate, and then we're able to use them to resolve a few things. Then here in group 5, we have nitrogen, we have phosphorus, we have arsenic, and so on, right? And in group 3, we have boron, we have aluminum, we have gallium, even indium too is somewhere around here, right? Indium and all the way, right? Just all the way. Now, should we, now, another interesting thing is we could combine elements in group 3 and group 4 to make some specialized semiconductor devices, probably for high-speed applications with improved temperature sensitivity. Okay, we don't want any device at room temperature, all the electrons begin to get excited and everything is energized, you know. So for us to be able to do that, then we could say something like gallium arsenide, right? Okay. Now, the idea about quantum well is that this deformity, which we call confinement, is a function of material difference. So let's assume we mesh in the fabrication process. Say we have aluminum, gallium arsenide here, then aluminum, gallium arsenide here. Then here we could have gallium arsenide, okay? Now, alternatively, we could also fabricate some other temperature sensitive materials that are a little resilient when it comes to temperature sensitivity, and then which we could use for high-speed applications. Say this is gallium arsenide. Let's assume this is gallium arsenide. Then let's say this is indium gallium arsenide. So this gives us a quantum well, okay? Because we realize the quantum well by embedding a thin layer of semiconductor medium between other semiconductor layers, okay? Now, why do we want to do this, okay? What was it meant for? What was it used for? Because this process is used for making quantum lasers, okay? We could make LEDs, okay? We could make photodetectors, even high electron mobility transistors. Because at the end of the day, we want to reduce the threshold current required to initiate lasing, like in lasers, thereby making the devices more energy efficient, okay? Such that the confinement of the carriers allow for faster response time, you know, making the quantum well laser suitable for high-speed communication. So we want to do that. So by this fabrication process, we still have to resolve the Schrodinger equation because those subatomic particles now have to drift into this. Now, by the time they drift into this, they require sufficient energy to be able to escape this region to this. And we want to keep them for a while here, okay? Now, and as such, this will lead to the derivations we are going to make relative to density of states. So then we now realize that we are going to be having quantized energy levels. This is where energy bands come in, E2 all the way, okay? So we now have the energy band gaps, okay? So that it will require that amount of energy to be able to move off, okay? And on and on. So now you should note that we already have made mention of the solution of the wave function in free space, where it is not bounded. But now we are going to consider the wave function in a bounded region. And as such, the solution is now going to vary. And don't forget, we already made mention of one interesting component that at this point, the wavelength is going to be described m minus v, okay? Because this potential operator now comes into play because we are in a bounded region, not in free space, okay? Well, we could go on and on and on, but I think now that we want to begin to talk in terms of things that are a little practical, then I would love to spare us a bit, but in this case, where we now have region 1, region 2, region 3, as we'll see shortly, then the Schrodinger equation will now be given as this of this, which will be the same as psi s epsilon. Recall we already resolved this, negative j e over h cross t, which will be the same as the energy of the wave in the second region, s of t, for instance, then which will be the same in the third region. Now you observe that we related the first region and the third region by the same expression, okay, because they are of similar material and they are not in any confinement, but the energy of the particle within the confinement is described differently, okay? So the reason for that, we are going to show in our next class. And then the mathematical rigor will try to resolve that and see how simple it is, okay? and then walk on, and then the current density and all of that, we try to resolve them, and then see how all of these things behave, and then resolve the density of states, and then look at the Fermi levels. Then we'll also talk about the quantum wells, the infinite and finite, and all of that. And then with that, we should be good to go, and then begin to look at more applications of this domain. So I think this is a good place to stop. So well, I will ask, any question, please, before I pass a few information. Any question, please? Okay. Okay, so in the absence of none, I think this is a good place to probably to stop, and then we try to review a few details.